Welcome to the third and final part of Unit 5. In this part, we're going to work two more 2D projectile motion problems. Here again is the slide on how to approach these problems, drawing pictures, writing grocery lists. In the first example we're working here, we're going to make use of symmetry. So here we have a ball launched from the ground at a speed of 30 meters per second and an angle of 60 degrees with respect to the vertical. So let's begin by drawing our picture. Standard XY coordinate system with positive X to the right, positive Y vertically. Gravity points downward, and the projectile is going to launch and come back down to the ground. And we're told that the initial velocity, the initial velocity here, V naught, is 30 meters per second at an angle of 60 degrees to the vertical. Okay, so two parts to this problem. How far does it go? So this is the answer for part A. And how high does it go? This value of Y is the answer to part B. Things we do know is it starts at a height of 0 because we can set it there. Starts at a position of 0 because we can set it there. Which means for part A, it goes back to that original height. And for part B, because of symmetry, we know it's going to be at its maximum point halfway through the total distance we found in part A. Okay. Anything else that we can label here? I don't think so. So we're going to end up with two grocery lists, one for part A. So I'm going to start with that one. Okay, things we can fill in right off the top. Acceleration in the y direction is negative 9.8 meters per second squared, and it's negative because gravity is downward. Acceleration in the horizontal direction is 0. Our initial horizontal position is 0, and the final position is what we want to know. Initial and final y positions for part A, how far does it land from its initial launch point, are both 0. We can draw our friendly triangle here. We know that this side is 30 meters per second. This is that 60 degree angle, which makes this side V naught X, this side V naught Y. So V naught X in this case is V naught sine of 60, which equals 25.98 meters per second. So I can fill that in up here, and because the horizontal acceleration is 0, I can put that in for Vx as well. V naught y is on the side adjacent, so V naught y will equal V naught cosine of 60, which is 15 meters per second. So I can fill that in as well. Because we have symmetry, we can also fill in this. Right? When it goes up, it comes back down at the same angle, but in the opposite vertical direction. So negative 15 meters per second in this case. Okay. We want to know position, X. But it's this horrible situation we have where in order to find X, we need to first find T. So to find time, we could use one of two equations. Because we have symmetry, we can use the Vy equals V naught y formula. But usually for these sorts of problems, we go to the y equals y naught formula. So y naught is 0, y is 0. V naught y was 15 meters per second, and there's the t we want to find, plus 1/2 of 9.8 meters per second squared. I forgot the negative sign. There it is. Times time squared. So 1/2 of 9.8 is 4.9. I'm going to move that over to the other side. So 4.9 meters per second squared. T squared equals 15 meters per second t. I can cancel one factor of time, which tells me that t equals 0 is a solution. So yes, the ball is on the ground when it starts. It's not a very helpful solution. The other solution is t equals 15 meters per second divided by 4.9 meters per second squared, which equals 3.06 seconds. So it takes 3.06 seconds for that ball to go up and then come down and hit the ground again. Now that I know time, I can find the total distance traveled. Okay, so x naught we let be 0. V naught x was 25.98 meters per second. And I multiply that by the 3.06 seconds. Plus 1/2 times 0 meters per second squared times 3.06 seconds squared. That last term is 0, and that leaves me with 79.49 meters. Okay, so remember, this is the time to go all the way across. So 1/2 that time is going to be 1.53 seconds. Okay. And we can make this argument that at its maximum point, it will take half the time to get there because we have symmetry. We can also say that the distance needed to go half, or to go to the maximum height, will be half of the total range, again because of symmetry. So with those two pieces in mind, we're going to work on part B now and write out its grocery list. Okay, so what do we know? We know our acceleration is still negative 9.8 meters per second squared. Our initial velocity in the y direction hasn't changed. That's 15 meters per second. Because we're going to the maximum height, the final y velocity is going to be 0. And I'm going to make a little note that that's at the top. Initial vertical position is 0. And the final height, y, is what we want to know. Due to symmetry, we can put in the 1.53 seconds for time. Horizontal acceleration is 0 meters per second squared, which makes the horizontal velocity constant at 25.98 meters per second, because that's the value that we found for part A. Initial horizontal position is 0, and final horizontal position we know because of symmetry is 39.75 meters. We want to know why, and we have a ton of information here. So for that, the easiest equation to use is the y equals y naught equation. So y naught is 0 plus 15 meters per second times 1.53 seconds plus 1/2 of negative 9.8 meters per second squared times 1.53 seconds all squared. And that works out to be a height of 11.48 meters. I hope you see in this example how acknowledging symmetry helped us to determine the answers for part B based on what we found in part A. And what we have here is a fire hose held near the ground, shooting water at a speed of 6.8 meters per second. What's not told us is the angle that the water lands at. We are told how far away it lands. And notice I have a little link there because we're going to need a trig identity to find this answer. Okay. So, again, drawing my picture. We have water. Oop, sorry, not sure exactly how that happened. Fired at 6.8 meters per second is our initial velocity at some unknown angle. It goes up, it comes down, and it lands 2 meters away. Okay. And so I can draw my pretty triangle. Here is V naught. Here is theta. V naught y, V naught x. And using that, I can now fill in as much of my grocery list as I am able. Oh, I again forgot gravity. There we go. T. Now we have some numbers in this problem. We are told it lands 2 meters away. We are given the initial velocity. I'm not going to put those numbers in place purposefully, because along the way we're going to derive an equation known as the range equation, which you might find potentially beneficial on the homework. It's not on the equation sheet, and I will not write a question that requires you to know it for the quiz. Okay. X component is on the side adjacent, so that makes it a cosine. And as we've seen the last 3 examples, horizontal acceleration is 0. So that makes our horizontal velocity constant. We put the acceleration in as a negative g, so that would be negative 9.8 meters per second squared. Initial vertical velocity is v naught sine theta. Initial vertical position is 0. Final and vertical position is 0. And we can even fill in what the final vertical velocity is because we have symmetry. And whatever it goes up with, it comes down with. So it's going down like this again at v naught, which makes this velocity negative v naught sine theta, because instead of pointing up, it's now pointing down. Okay. Remember, the only 3 numbers we know is we know what g is, we know what x is, and we know what v naught is. And from this information, we can actually get angles out. Okay. So, it's again a situation of the information I have numbers for is the horizontal position. And to be able to use that equation, I have to know time. So the first thing I'm going to do is start with the vertical motion to find equation for the time of flight when we have symmetric motion. Okay, initial position was 0. V naught y was v naught sine theta. Time is what I want to know. Final position was also 0. Minus 1/2 times gt squared. And this is, without numbers, the exact same math we did on the previous example. So I can say that 1/2 g times t squared equals v naught sine theta times t. I can cancel one factor of time and get t equals 0 as a possibility, but again, that's just telling me that it's on the ground when it starts. The other root looks like t equals 2 v naught sine theta divided by g. And this is time of flight and is valid whenever your starting height equals your ending height. So when you have symmetry. Okay. I can now go over to the horizontal equation. And plug in my time formula that I just found. Initial horizontal position was 0. Initial horizontal velocity was v naught cosine theta times my time, but remember the time formula I just found was 2 v naught sine theta divided by g plus 1/2 times 0 meters per second squared t squared. And yes, I could write that all out again, but this whole term goes away. And I'm running out of room, so I'm not. Okay, so now I'm just going to multiply this out and regroup it a little bit. And what I find is I have a v naught here and a v naught there. So that's v naught squared divide by g all times 2 sine theta cosine theta. And that equals my total horizontal distance, again, when I have symmetry. Remember, the goal of this problem is angles. And right now, angles are buried in a sine multiplied by a cosine. But remember I said there was a trig identity. So if we open up this lovely table of trig identities and scroll down to the double angle formulas. Look, we have sine of 2u equals 2 sine u cosine u. And this 2 sine u cosine u is exactly what we have in our formula right now. So I can write, based on the trig identity, so there's a trig identity, that 2 sine theta times cosine theta equals the sine of 2 theta. And plug that in. So now I have x equals v naught squared over g times the sine of 2 theta. This formula is known as the range equation and is again only valid when you're dealing with a situation where you have symmetry. And notice the only things that are left in here are horizontal position, which was given in the problem as 2 meters, initial velocity, which was given in the problem as 6.8 meters per second, and the acceleration due to gravity, which is 9.8 meters per second squared. So I know everything here except the angle, which is what I want to find. So I'm going to rearrange that formula and solve for sine of 2 theta. So sine of 2 theta is going to equal g times x divided by v naught squared. Okay. And I can plug in numbers, so that's 9.8 meters per second squared times the 2 meters that was given in the problem divided by 6.8 meters per second, the whole thing squared, which the initial velocity was also given in the problem. And when you multiply and divide all this out, you get 0.42. Now, at this point, you could do this, and you could say, okay, well, if sine 2 theta equals 0.42, then 2 theta equals the inverse sine of 0.42, which equals 25.08 degrees, which means theta equals 12.54 degrees. And that is a possible answer. But if you only do that, you are missing a possible solution. Okay. If you think graphically of sine of an angle, I don't want to use theta in this case, plotted as a function of that angle. It starts at 0, goes up, comes down, goes up, and this would be the 90-degree mark. This would be 180, and this would be 360, and it runs between a maximum of 1 and a minimum of -1. Okay, I have sine of, if you will, phi 2 theta equals 0.42. Well, that's about halfway in between. And notice there are two possible angles, one on either side of 90 degrees, where that statement is true. We just found this one, 25.08 degrees. But that means that there is a second possible angle. Okay. And that second possible angle right here, remember symmetric about 90 degrees, is going to be 180 degrees minus 25.08 degrees, which equals 154.92 degrees. So I could have 2 theta equals 25.08 degrees, or I could have it equaling 154.92 degrees, which means theta equals 12.54 degrees, or it equals 77.46 degrees, right? And notice, just as the 2 theta angles were symmetric about 90, your theta angles are now symmetric about 45 degrees. And recall, I think it was in part 1, we looked at the simulation and found that there were 2 angles that could go the same distance. One was low and the other one was high. And we just found those 2 angles for this particular situation. This concludes part 3 of our study of 2D projectile motion. It also completes Unit 5. In the first 5 units, we've been very focused on position, velocity, and acceleration. We've looked at it for projectile motion. We've looked at it in one-dimensional motion. We've looked at it just in general. And never in any of that analysis have we looked at why that motion is happening. We just assumed it was. When we move on to Unit 6, we're going to introduce the concept of force, which allows us to think about how motion actually happens.